In this lesson, we're going to learn how we can use percent composition to determine the formula of a substance. So the most useful thing about percent composition information is that if we know, or percent composition is known, we can use that to determine the empirical formula of that substance. So remember that our empirical formula is the simplest whole number ratio of atoms. So this is really giving us the mole ratio of atoms of each type. What percent composition gives the relative masses of each element. So percent composition is in terms of mass, empirical formula is in terms of moles. Essentially all we need to do is convert mass into moles and find the ratio in order to get our empirical formula. And how do we convert grams to moles? Molar mass. So all we really need to do is convert our mass percent to moles and find the ratio. So use molar mass. Yeah. So for example, let's say an oxide of chromium is found to be 68.4% chromium and 31.6% oxygen by mass. And we want to determine the empirical formula. First thing we need to do is to convert our mass percents into moles. So essentially what we're doing is assuming we have a 100-gram sample. If we have a 100-gram sample, technically you can use any sample size, it's just more math if you use anything else. But if we assume that we have a 100-gram sample, then our percentages are going to be equal to the masses that we have. If we had 100 grams of this oxide, we would have 68.4 grams of chromium in that sample, because 68.4% of 100 is 68.4, and we would have 31.6 grams of oxygen in that sample for the same reason. So we can convert our mass percents to moles using our molar masses. So for chromium, what that's going to look like is we know that this is 68.4 grams, or 68.4% chromium by mass. So let's say we have 68.4 grams of chromium. Oops. We need the molar mass of chromium from the periodic table, which is 51.996 grams, is equivalent to 1 mole of chromium. So that tells us that in that hypothetical 100-gram sample, we would have 1.315 moles of chromium. We can do the same thing for oxygen. We know that this is 31.6% oxygen by mass. So if we had 100 grams of the whole sample, of the whole compound, we would have 31.6 grams of oxygen in that sample. And the molar mass of oxygen from the periodic table tells us that 15.999 grams of oxygen is equivalent to 1 mole. Which means that we would have 1.975 moles of oxygen. So once we know we've converted mass to moles here, what we need to do is find the ratio. Because that's what our empirical formula really represents, is the ratio of atoms, that for every one of these we have 2 of these, or for every 3 of these we have 7 of these, whatever the case may be. We're determining the ratio between those two things. So it doesn't really matter how many specific moles you end up with. What matters is the relative amount of moles. So generally we want to take the bigger one and divide it by the smaller one. If there's more than 2 elements, you'll end up kind of determining multiple ratios and have to put them together at the end. But for this one, you just have one relatively simple one. So if we take the bigger one and divide it by the smaller one, we have 1.975 moles of oxygen for every 1.315 moles of chromium. If we do that division, what we end up with is a ratio of how many moles of oxygen are there for every 1 mole of chromium. And what it comes out to be is about 1.502. And this is where determining empirical formulas gets a little bit wishy-washy sometimes, because we're looking to get to integers. Ultimately, we know our subscripts in our empirical formulas can only be integers. 1.5 is not an integer, and it's not close to an integer. It is squarely between 1 and 2. So what we want to kind of look for at this point is that we want to round this to an integer if it's close, or some kind of simple fraction that we can multiply things and make it be an integer. So by simple fraction, I'm talking like a half, a third, a quarter, maybe a fifth, but even that is getting like a little bit too specific for a lot of things. So 1.502 is very, very close to being 1.5 moles of oxygen per 1 mole of chromium. There we go. So we're still not at an integer, but we're at a place where we can clearly get to an integer. If we multiply the top and bottom by the same factor, we're not changing the value of the ratio, we're just changing the way we're expressing it. So in this case, since we have 1.5 over 1, if we multiply by 2 over 2, sorry, I don't know why that keeps happening. If we multiply by 2 over 2, we get this in terms of nothing but integers. So 1.5 times 2 is 3, 1 times 2 is 2, so 1.5 over 1 is the same as 3 over 2. So now we have an integer ratio, and that ratio just needs to get translated into subscripts. So that ratio is telling us that there are 3 moles of chromium for every 3 moles of oxygen for every 2 moles of chromium in this compound. So those numbers are going to become my subscripts in the formula. 2 moles of chromium becomes this 2. Let's not do colors that are that similar. 3 moles of oxygen is where this 3 is coming from. So by figuring out the ratio of moles of different types of elements in our compound, we are then able to just kind of translate that into a formula. Now, to find a molecular formula, we need one other piece of information. And that piece of information is the molar mass. So remember that the empirical formula gives us just the simplest whole number ratio of atoms of each element. Our molecular formula gives us the exact number of atoms of each element. So to figure out the molecular formula, we need to know the total mass of the thing. Just percent composition by itself can only give us the empirical formula because it only gives us the ratios. To figure out the exact total number of atoms, we need to know the total mass of the thing. So for example, let's say we've already figured out the empirical formula, that if we have a compound with an empirical formula of CH2O, and we find that it has the molar mass of 150-ish grams per mole. That is enough information to determine its molecular formula. So essentially what we're doing here is figuring out how much bigger, how many times bigger is the actual molecule than the empirical formula. So this isn't an official term, but the way I approach this is to figure out what is called, what I refer to as the empirical mass. Again, not really an official term, just the mass of the empirical formula. Our empirical formula being CH2O in this case, would be the mass of carbon plus 2 hydrogens plus oxygen, which gets us a total of 30.026 grams per mole. So if we take the molar mass, which we were given as 150, and divide that by the quote-unquote empirical mass, mass of the empirical formula, we get something really, really, really close to 5. It comes out to like 4.9999 or something. But really, really close to 5. Again, you want to be rounding to like an integer here, and it should come out close to an integer. So we've got the molar mass, which is the mass of the molecular formula. We're dividing by the mass of the empirical formula. And what that tells us is that the molecule, the molecular formula, is 5 times bigger. So what we are going to do is multiply all of these subscripts by 5. So if my empirical formula was CH2O, my molecular formula, 1 times 5 is 5, 2 times 5 is 10, 1 times 5 is 5, is going to be C5H10O5 is my molecular formula.